Alright guys, so again on part C, we were trying to find our stopping potential, which is VO. So I have Kmax equals E times VO. We already knew our Kmax. We calculated that in part A, and that was 4.2 times 10 to the negative 20th. I know my E is just the charge of the electron, so that's 1.6 times 10 to the negative 19th. I can then find VO by dividing both sides by this number. So let's do that. If I divide both sides, so I'm going to end up taking 4.2 times 10 to the negative 20th and dividing it by 1.6 times 10 to the negative 19th. And when I do that, we should get we should get 0.263 volts, because stopping potential, electric potential, think voltage, so stopping potential would just be in volts. So my answer should be 0.263 volts, okay? So again, I think that that would be a really good free response question for you guys, because they're trying to bring in tons of stuff that you've learned from multiple chapters, okay? So like in part A, we were given the wavelength, but we still had to find energy. Also in part A, they gave you the work function, but they gave it to you in electron volts, and you had to know to convert that into joules. So a lot of stuff I think that they're testing you on. In part B, they wanted you to realize that you needed to use the kinetic energy, and that the mass would be the mass of the electron. So lots of good stuff there. Okay, so let's keep going on. I'm on slide number 18. Which is still, this is where it's talking about the cutoff frequency. So this says that the cutoff frequency, below which no electrons will be emitted no matter how intense the light, is given by a certain formula here. I can find the frequency, and that would be equal to taking the work function, so the amount of work that's done, and dividing it by Planck's constant. Okay, so we can find the cutoff frequency where there will be no more electrons that can be emitted. So electrons will no longer be emitted from a material no matter how bright or how intense the light is. And I can find that by taking the work function, by taking work and dividing it by h, which is just Planck's constant. Okay, I think the next slide, number 19, yes, is going to be an example of this. So let's do that. Okay, in slide 19, they are saying the work function of a particular metal is measured to be 2.5 electron volts. What is the minimum frequency of light to emit photoelectrons? And then it asks what is the longest wavelength, or what is the longest corresponding wavelength? So we want to know two things. We're trying to solve for two things. First, I need to find what the minimum frequency of light to emit photoelectrons would be. They gave me the work function. So I know that my crazy little Greek symbol is equal to 2.5 electron volts. But now we don't want that in electron volts, we want that in joules. So I know right now my theta equals 2.5 electron volts. I am trying to find that cutoff frequency. So I know my formula is frequency equals the work function over h, which is just Planck's constant. Do we know this number already? You should be saying yes, we do, because it's going to be in the front of your test book. So my h is just that 6.34 times 10 to the negative 34th. We already know that. And let's write that down too. So h equals 6.63 times 10 to the negative 34th, and that's a joule second. Okay? So I know both of these things. The only problem is this is in joules and that's in electron volts, so I need to get this into joules because these numbers, these units don't correspond with one another. Now, just like in the last problem that we did, there's a conversion factor that says 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So we were given that conversion factor and we've used that before, so we're going to have to use it again. So let's set this up. 2.5 electron volts. We want to go to joules. So that means my electron volt needs to be on the bottom because I'm trying to divide it to cancel it out. So I know 1 electron volt, there's 1.6 times 10 to the negative 19th joules. So here's my conversion factor. I'm going to take 2.5 and multiply it by 1.6 times 10 to the negative 19. Okay, when we do that, guys, our new work function will be 4 times 10 to the negative 19th joules. So all I did is just convert to joules instead of leaving it in electron volts. And I had to do that because my H is in joules, okay? So now I have H, I have work. I have H, I have work. I can find frequency, so let's do that. So I'm going to take my work function, which was 4 times 10 to the negative 19th. I'm going to divide that by my Planck's constant, which is 6.63 times 10 to the negative 34th, and that's joule seconds. So here's what it should be set up. Frequency is equal to my work over Planck's constant. When we divide them, you should get 6.03 times 10 to the 14th, and let's look at this. Joules are going to cancel. So my joules here cancel, which means I'm left with a per second, which is exactly what frequency is measured in. So per second is the same thing as a hertz. And that's why we have 6.03 times 10 to the 14th hertz. Okay? Now, that's not the end of the problem because they've also asked me what is the longest corresponding wavelength. So I know my frequency, and my frequency is 6.03 times 10 to the 14th hertz. I'm trying to find, and remember now this is light, so I know the speed of light in a vacuum is always going to be 3 times 10 to the 8th meters per second. I'm trying to find lambda. So I have these 3 things. I have these 2, I need this one. Is there a formula that corresponds all 3 of those things together? There is. This one. So C equals F times lambda. So let's go ahead and plug everything in. I know C is 3 times 10 to the 8th. I know my frequency is 6.03 times 10 to the 14th. And I'm trying to find my wavelength. So to get lambda by itself, I divide both sides by the frequency. So let's do that. Okay guys, when you take 3 times 10 to the 8th and divide it by 6.03 times 10 to the 14th, you should get 4.98 times 10 to the negative 7th meters. So that's our answer. Now sometimes you know, especially on those multiple choice questions that they ask you stuff like, maybe you get it solved for 4.98 times 10 to the negative 7th meters, but let's say they want it in nanometers. So if they want it in nanometers, all I have to do is what? What do I do here? Do we know? If I want this in nanometers, I'm just going to divide that number by 10 to the negative 9th. So when I do that, it should be 498 nanometers. Now, we know that light, visible light, is in the range of 400 to 700 nanometers. So this is just to show you that this light that's being emitted is within the visible spectrum, okay? All right, let's keep going. So we're moving now to Arthur Compton's research, which is all about wavelengths. So Arthur Compton in 1923 observed that when a beam of monochromatic X-rays, you're probably thinking, what does monochromatic mean? That just means that it's a single wavelength. So monochromatic just means like it's a single ray. It's like a single wave. So Arthur Compton observed when a beam of monochromatic X-rays were scattered by various materials, that the wavelengths of those scattered rays were longer than what initially hit the object. So let's see. Okay, let's just say this is some various material, and there's a wave, there's particles that are getting ready to strike that material. So I have some type of waves that are coming in and they're going to hit this object, they're going to hit this material. So this is what they mean by like the incident wave. So this wave comes in, hits the object. Now what Compton found was that when a single wave would hit a piece of material, then when that wavelength leaves the object, it's going to be scattered and the wavelength's going to be longer. So okay, so here was my wave when it hits the object. Now my wavelength is leaving. This wavelength is much longer than the wavelength between these two. So just like between here, that's a shorter distance compared to this to this. So that's what he found, was that when a wave, especially, and in particular he used X-rays here. So when an X-ray hit a material, and it didn't matter what type of material it was, when the X-ray hit the material, then that scattered X-ray, or the one that's leaving that material, is going to have a longer wavelength than the one that did before it hit the material. Okay. Compton said that the type of material didn't matter. So like whether this X-ray hit wood or whether that X-ray hit metal, it wouldn't matter because the wavelength that leaves that object is going to be longer regardless of whatever material it is. So he said that the reason that there was a change in wavelength was more due to the angle at which that wavelength was leaving compared to instead of just the material itself. Okay, so we're going on now to slide number 21, and this says, according to wave theory, any scattered radiation should have the same frequency and wavelength. Compton, when he was thinking about this and working on this, he knew that Einstein wouldn't necessarily be happy, because he thought that according to Einstein's theory, if the frequency changes, then the amount of energy must also have to change. Because think about this. According to Einstein, energy is equal to h times f. Energy is equal to Planck's constant times frequency. So that means that energy and frequency are directly related here. So if frequency changes, energy is going to have to change too. So Compton started to think about different types of collisions. And Compton thought that photons act more like particles when they collide with electrons. If a photon collides with an electron that's initially at rest, then the photon should have to transfer some type of energy and momentum. So because of this, the energy has to decrease, which means that you're going to get a longer wavelength. So again, let's kind of talk this over again. According to Compton, or according to wave theory, let's even just go back to wave theory. According to the wave theory thought that Compton was crazy because wavelengths really shouldn't be getting longer. They should be staying the same. Because according to wave theory, everything has to have still that same amount of energy.